Hello everyone and welcome to Carlum Cymru revision sessions. This session this evening will focus on mechanics projectiles and will be at A level and will be presented by Mr. Weatherhead of Porthcawl Comprehensive School. The session will last around 45 minutes where Mr. Weatherhead will run through relevant content. If you have any questions during the session, please use the question and answer section and we'll do our best to answer you. You will see that there's a hyperlink in the question action section. If you're happy to leave your name and email address, we would love to keep in touch with you so that you can send you more information about future events. You can click on the link at any time during the session. Today's session will be recorded, and the recording, any relevant resources will be uploaded to the e-sgol website under the Carlum Cymru tab. Thank you. Over to you, Mr. Weatherhead.
Thank you, Mr. Mackenzie. Okay, so we're on to projectiles today. And we'll just start with a few different sort of scenarios here. They're all on flat horizontal ground. Okay, so this first problem is what I'd call a symmetrical problem. The way up and the way down are basically mirror images of each other. Okay, in a practical real life context, this could be a golf ball being hit from the floor and then landing further down. Okay, and there's a few things to just be aware of. As we are going up, we are losing velocity, losing speed, okay, because of gravity. When we get to the top here, just like at AS, our vertical, so our V vertical, okay, our vertical speed, our vertical velocity is actually 0, okay, so that's still for AS. And then on our way back down, we're getting negative velocity, so we're losing velocity, but we are gaining speed. Okay, so it's getting faster, and it's getting faster at the same rate as it got slower on the way up. It's all due to gravity. Okay, and I would describe this then as a symmetrical problem, and that's really handy actually, because what it means is the time taken to get to the top up here is exactly the same as the time it takes to get back down here. So you can just double the time, and you've got how long it was in the air. Okay, and we call that time of flight. It also means that whatever velocity I gave it and whatever angle it was launched at, that's exactly the same when it lands. Okay, so if it goes up at an angle of, let's say, 80 degrees at 30 meters per second, then when it lands, because it's symmetrical, it comes back down at an angle of 80 degrees and it comes back down at a speed of 30 meters per second. Okay, so that can really speed problems up if they are symmetrical. Bit further down here then, so this is an example of like a ball, a particle. It's starting from higher up this time, so it's not symmetrical. Okay, we've still got this condition at the very top here of vertical speed equals 0, but the time taken to do this little bit is going to be a lot less than the time it takes to come back down there. Okay, and because it's falling such a long way, it's going to gain a lot more speed on the way back down. Okay, a practical example of that might be a tennis player serving the ball. So the ball is already sort of 2.5, 3 meters in the air when it's struck. Okay, and it lands the other side of the net. Or it could be like in cricket, the bowler comes in and throws the ball from up high and it bounces further down the wicket. Okay, and then we've got our third type of sort of projectiles question down here, where we're not interested in where it lands. Okay, obviously it will land, but maybe we don't even care about getting that far. So maybe this is sort of a shot in football, and the issue is whether it's going to go in the goal or whether it's a kick in rugby, and is it going to cross over the post if it's a rugby one like that. Okay, and maybe what you'd be more interested in there is the speed and the direction at any given time during the flight. So rather than finding the range, which is how far away it lands, or the time of flight, which is how long it takes to land. Okay, so 3 different types of question, all slightly different. Okay, the symmetrical ones are the easiest ones to work with. Okay, so the basics of projectiles then. So there's a couple of ways you can be given the information. It's not unusual to see an initial speed given, so u, and an angle. So it might be that a cannon is fired at 50 meters per second at an angle of 20 degrees. Okay, and what we would be interested in there is the vertical and horizontal components. So if this is our hypotenuse, this is our opposite, this is our adjacent, there's our right angle. The vertical component would be u sine theta, and the horizontal component would be u cos theta. And that's important because when we work with projectiles, we are always working separately between the vertical and the horizontal. Okay, so if you get given a question like that, your first job will always be to find those components using trigonometry, sine and cos. Okay? Another way you could be given the information is as a vector, and that's better because it does save you the job of finding your components, in which case, now probably won't be drawn, and that is meant to be vertical. Let me straighten that up a little bit there. Okay, so you might be told that it's been given an initial velocity of 20I plus 6j. So the I direction is horizontal, so this is 20 meters per second, and this is 6 meters per second. Okay, or if it was on its way down, you might get a negative j value. Okay, and that saves you, like I say, the job of sorting out your triangle. And now this is on the way back down, so this is towards the end of a projectiles question, where you may know the horizontal and you've worked out the vertical, so that might be minus 15, let's say, for instance, but you're being asked to give the speed. Okay, so this is sort of the opposite of this top one up here, where you were given the speed and the direction, and we split it up into its components. Now down here at the end of a question, we've got the horizontal and vertical components, and what we're interested in is the actual speed. So speed is the resultant, it's the magnitude, it's the length of that hypotenuse. Okay, so the speed in this case would be the square root of 8 squared plus 5 squared. Okay, that would be 17 because that's a Pythagorean triple there. Okay, and then to get the angle, normally we measure angle with the horizontal, so it would be that one. And I would then use tan. I'd prefer to use these components because more often than not, they will be more accurate than this Pythagoras answer here, which has been rounded. So this is my opposite, this is my adjacent, and I would be doing that theta equals tan to the minus 1, and that'd be 15 over 8. And you can ignore the minus, just like I did on Pythagoras, because we are just finding the angle. We know it's a negative angle from our diagram. In that case, it would be 61.9 degrees to the horizontal. Okay, but if you've got a diagram that shows the examiner, you know the direction, all you need is the number. So that's why it doesn't matter about having the minus up there. Okay, so that's the basics. If we actually have a look a bit more in depth at the question now then. So this is a projectile that's being fired at an initial speed of 30 meters per second at an angle of 42 degrees. Okay, and there's a couple of things you need to know. So first of all, I've split my page in half, and that's a good strategy because it does keep your work in separate. It saves you picking the wrong number for the wrong direction. Horizontal and vertical are independent of each other. Okay, so on the horizontal side, the most important thing to know that this value here, this u cos theta, is constant. It does not change at any point during the question because we are using a particle model and we're ignoring air resistance. Okay, so u cos theta, once you know it, or the I direction if it's a vector, is constant. Because it's constant speed, we don't need to use any Suvat equations. We can just simply use speed equals distance over time or any of the rearrangements of that. Okay, so distance equals speed times time, or time equals distance over speed. Okay, so the horizontal direction we often find is easier to work with. The vertical direction, now that's different. Because in the vertical direction, gravity is constantly pulling us back down, and on our way up, it's decelerating the particle. Now we do need to use Suvat equations. So in the vertical direction, we will use Suvat. And then what you've got then, the one thing that links these two, they're independent of each other, but the one thing that links them is the time. Okay, so if you've calculated that the golf ball, the football, the cannonball, the tennis ball is in the air for 3.5 seconds, then that applies to the horizontal and the vertical. Okay, now where you get that value from varies from question to question, but once you've got the time for either horizontal or vertical, you can then transfer it over, and sometimes then that unlocks the next bit of the problem. Okay, so what we're going to do on this question is we're actually going to do some working out now then. Okay, so same thing. So if I replace, then we've got 32 up here for you, and we've got 30 up there for you, and 42 for our angle. And we're going to do three things. We're going to find the time of flight, so how long is it in the air for? And we're going to find the range, and range means how far away does it land. Okay, I'm keeping all of these on horizontal ground, otherwise you'd need to take into account the slope. And we're going to find the speed and direction of the particle after 3 seconds. So we're going to work out, is it going up or down? How quickly is it going? And what precise angle is it traveling at that moment in time? Okay. With projectiles, a nice way to think about it is like watching a video of a golf ball, a cannonball, and being able to pause the video at any point you like, and then asking yourself what is going on at that moment in time. Okay, it's just a sort of a freeze, a photo, if you like. Okay, so what do we know? Well, I've first of all got to do my vertical and horizontal components, my I and J components. So we've got 30 sine 42 up here. And what I'm going to do, I mean, if I want to be super accurate, I could leave everything in terms of 30 sine 42. But what I'm going to do, I'm going to actually work them out. Okay, so everyone's a bit happy with numbers. And what I'll do, I'll leave a few more decimal places on there. At the end, we round to 3 significant figures. So as long as I work a little bit more accurately than that, we should be okay. And then down the bottom here, we've got 30 cos 42. And again, I'll work that out and I'll keep a few decimal places. So that's 22.294. Okay. But if you want to be really accurate, like I say, you can work in terms of sine and cos. It's not a problem. It's just a bit more fussy when you're typing things into the calculator, and it makes the explaining easier for me if I don't do that. Okay, so what do we know? The horizontal direction. Remember, this is speed, distance, time on this side. So we know the speed. The speed is 22.294. We don't know the distance, we don't know the time. So as far as the horizontal direction goes, we are stuck there. Vertically, we know quite a lot more. If we set u, which is our initial vertical speed, that's 20.074. Okay. We've got the acceleration is minus 9.8. And if you remember back from year 12, to use SUVAT, you need three things. Well, I don't know the time of flight. I don't know how high it gets. So that takes out S and V. Okay, or sorry, S and T, so how long it takes to get there. What I can do is say, well, at the top, at that highest point, V will be 0. So what I'm actually going to do is not do the entire time of flight for now. I'm just going to get up to that highest point. Okay, now I can say then I want to find T first. Okay, so I'm going to use V equals U plus AT. So 0 equals 20.074 minus 9.8t, because on the way up we're decelerating, and we get a time of 2.048 seconds. Now remember, that is just the way up. This problem is symmetrical because it's flat horizontal ground. Okay, so the total time that it's in the air is double that. So that's 4.10 seconds rounded to 3 significant figures. Okay, and now I know the time of flight, I can transfer that over here. So 4.10 seconds, and this is meters per second there. Right, well, this is speed, distance, time. Now I can work out the distance. So the distance is speed times time. So that's 22.294, oops, times 4.10, and that gives us 91.3 meters. So I've actually done the first two questions. How long is it in the air? 4.10 seconds. Okay, that's 2.05 on the way up, 2.05 on the way back down. I found the range, because in that time it will travel 91.3 meters horizontally. Okay, so there's the first two done. Now I need to find the speed and the direction of the particle after 3 seconds. And actually for that, I'm going to start again, because everything I've done so far there is all to do with going all the way up, all the way back down. Now I know that after 3 seconds, it's going to be on its way back down, because it's longer than 2.05, so it's on its way back down. So nothing I've done really helps. So what do we have? Well, the horizontal doesn't really change. That speed we had in the first section is exactly the same. So I know the speed is still 22.294. Remember, that's constant, it doesn't change. Vertically, if I start again, U is 20.074. A is still minus 9.8. Okay, but this time we know that the time is 3 seconds. Now we are interested in finding the speed and the direction. So I want to work out V. So I'm going to use V equals U plus AT for that. Okay, so that's 20.074 minus 9.8 lots of 3. And that tells me that the velocity is minus 9.326, which just proves what I said, that it is on its way back down. A negative velocity in this case means we are falling. Okay, so how do I find speed and direction? Well, at the minute, I've got 2 speeds. I've got one horizontal and I've got one vertical. Technically, they're velocities. Okay. To turn them into a speed, what I need to do now is to form a triangle with those values. So we have got 22.294 as our horizontal. That hasn't changed at all in this question. And look, when the time is 3 seconds, our vertical is minus 9.326. Not that the minus is going to make much difference when we do our workings. And what do we want to know? Well, we want to know the speed. That's our hypotenuse, our magnitude, okay, the resultant. And we want to know the angle in there. So a little bit like on my earlier slide, it's Pythagoras, and it's going to be tan. So if we do the speed first, the speed is just going to be the square root of 22.294 squared plus 9.326 squared. You could ignore the minus, it would come out when you square anyway. So the speed is 24.7 meters per second. Okay. I mean, that's what it's really doing. Okay, that's what it's really doing. And the angle that it's coming down at is going to be tan minus 1 of 9.326, which is our opposite, over 22.294, which is our adjacent, and that's an angle of 22.1 degrees. Okay. Now that's just a freeze frame, a snapshot when the time is 3. If you kept the video going, if you kept the time going, what would happen? Okay, well, the 22.294 is not going to change. That's constant. But the 9.326 is going to increase. Okay, it's going to get to 9.4, 9.5, 9.6, 9.7 until eventually it hits the floor. Okay, so that's going to have 2 effects. The overall speed, the hypotenuse, is going to get bigger and bigger. Okay, so it's going to get faster as it falls, which is common sense, but also because the horizontal is fixed and the vertical is growing, this angle is going to get bigger and bigger as we fall, and that's what gives you the curved path. Okay, so as we're falling, if I draw some tangents on here, we go in that direction, then we go in that direction, then we go in that direction, and then we go in that direction, and these arrows are getting steeper and steeper because the vertical component is getting bigger and bigger. Okay, and that's what generates the curved path, which is called our trajectory. Okay, here's my next question then. So we are kicking a ball towards some goals. The goals are 18 meters away and the ball is kicked at an angle of 15 degrees. Okay, and what we want to know is, firstly, does it go under or over the crossbar? So have we scored a goal? Seeing it's on target, have we scored a goal, or has it ended up in the crowd? And when it goes into the goal, or when it goes over the bar, how quickly is it traveling at that point in time? Okay, So where do we start this time? Well, split your page. Remember, you can pause these videos at any time you like now. Have a go, and when you press play, it will just pick up from where you pause. You won't miss anything. Okay, so if you want to pause the video and have a go. Okay, horizontally speaking, we know the distance to the goal is 18 meters. Okay, and if I put a little triangle on here, we were given quite a lot of information here as well. So the speed of the ball was 25 meters per second, and the angle that it was kicked at was 15 degrees to the horizontal. Okay, so if I put my triangle in there, we've got 25 sine 15, which is 6.47 vertically, and we've got 25 cos 15, which is 24.148. Okay, and then if we put those values in underneath, so horizontally, our speed is 24.148, and vertically, now remember this is our initial speed because we've only just kicked it, vertically 6.47, we'll say that up is positive. Okay, A is minus 9.8, that's always going to be true. And at that point on the right hand side here, the vertical is stuck. Okay, because vertically, I don't know how high up it goes, we're trying to work that out. Okay, I don't know how long it's in the air for, and I don't know the speed it's going to get to. I mean, I could work out the highest point, but that's not what we're trying to do here. Look on the left hand side, we're going to work with the horizontal. Remember, this is speed, distance, time. Well, we've got 2, so we're good to go really. Time equals distance over speed. So that's 18 meters divided by 24.148 meters per second. So it's going to take the ball 0.7454 seconds to get to the goal. Okay, that's how long it's in the air for, and then at that point the ball will be at the goal. Now we still don't know whether it's gone over the bar or under the bar, but because I've got a time value now, I can fill that time value in over here. Okay, so that goes in there, and now I've got my 3 things. What am I interested in? Well, actually, I want 2 things. I want, does it pass under or over the crossbar, which is 2.3 meters high? So I want to know vertically, I want to know its displacement S. So if we do that first, okay, I'm going to use UT plus a half AT squared for this. So 6.47 lots of 0.7454, that's my UT, minus 4.9 is my half A, 0.7454 squared. So there's my half AT squared part. And if you put that in the calculator, you get 2.1 meters. So my ball is in the goals. Okay, right in the top corner with 20 centimeters to spare. So a great shot. Now we need to know the speed when it goes past the goal posts. So I need to know V. So remember now, speed is scalar. So that means I need to form a triangle and find that hypotenuse. Okay, it's not enough just to have it in horizontal and vertical. We need to get that one single value for speed. So I need V. Okay, for that I'm going to use V equals U plus AT. The same 3 values I had to start with. So that's 6.47 minus 9.8 lots of 0.7454. And we get a vertical speed, of minus 0.8349. What does that tell me? The ball has gone past its highest point and is actually on its way back down. So if I get rid of some of this now, let's delete that because it's kind of in the way. We've got all these numbers, haven't we? What's happened is, let me get rid of that. Okay, so we've gone up. We've reached our highest point, somewhere around there-ish, and the ball is actually falling back down again now. Okay, it's on its way back down. If I form a triangle with what I know, so horizontally, we've known all along, that's 24.148. Vertically, we're on our way back down, and that's minus 0.8349. And then it's just Pythagoras again and trigonometry again. Okay, I won't do the full workings this time. So Pythagoras for the hypotenuse, you get 24.2 meters per second, not that much bigger than the horizontal because the vertical component is tiny. Okay, and you get an angle, so that's my emails going off, and you get an angle, if you work the angle out, 2 degrees. So in other words, only just on its way back down. Okay, so this is soon after its highest point, so coming back down at an angle of 2 degrees. Okay, now then, what could affect our answer? And you'll often get asked these questions, you've done all your workings out, and then they throw in a part C or part D, explain any assumptions you've made, explain the impact this has on your answer. Well, the particle model always ignores air resistance. What effect would that have? Okay, well, if we included air resistance, the ball would take longer to get to the goal because it's going to lose horizontal speed as it goes rather than it being constant. That means it's in the air for longer. If it's in the air for longer, it will fall further. Okay, so 2 impacts. It'll take the ball longer to get to the goal, and it'll drop a little bit, so it won't be 2.1 meters off the ground. Okay, the other one you could include there as a possible assumption is we've ignored the spin of the ball. Okay, if you put spin on a football, you can cause it to bend left or right. You can cause it to dip faster than it normally would. Okay, and the other one, which is a little bit more subtle, is ignoring the size of the ball. So when I say I've gone just under the crossbar, if the ball is actually sort of 30 centimeters diameter and I've only gone under the crossbar by, let's say, 5 centimeters, well, the ball is going to hit the crossbar, isn't it? Because the radius is 15 centimeters. If the middle of the ball is only 5 centimeters below the crossbar, a large chunk of the ball is actually going to hit the bar. Okay, so a couple of assumptions you could include there. Okay, air resistance, spin, and the size of the ball itself. Okay, next question. Now this one is different because this is an example where the ball is starting up in the air this time, we're not on the ground, and this is a cricket one. Okay, sport close to my heart. A bowler releases a cricket ball from a height of 2.5 meters. Okay, so remember, you can pause the video, and if you want to have a little go, that would be brilliant. Okay, you'll definitely learn more from having a go than just watching. So 2.5 meters up in the air by the time they've lifted their arm up and stretched a little bit. And this time we've given our initial sort of values in vector form. So we've got an I component, a horizontal component of 35 meters per second. I'm not going to put it in the units because we can get a bit cramped up here. And our vertical is -3. So that means when it leaves the bowler's hand, the ball is already coming down. All right. Rather than coming out horizontally, it is already dropping. Okay. We're going to calculate the speed of the ball when it bounces. So we assume then it's going to bounce over here somewhere. Okay. And the horizontal distance when it bounces. So how far down the pitch before it bounces. So that's almost like the range, if you like. Okay. So what do we know? Horizontally, we know the speed is 35, and vertically, now since this ball is only going to come back down and we're not worried about it coming back up, what we could do now is just take down as positive. It'd make life a lot easier. So I'm actually going to just say that U is 3. Okay, and we'll say down is positive. It's not going to matter because we're not planning on coming back up anyway. So in that case, A is positive 9.8. Okay, and we know that the ball when it bounces will have fallen 2.5 meters. Okay, all in SI units. So we know more in the vertical direction than we do in the horizontal. So this time we're going to start on the right hand side. We're going to do our vertical workings first. Now there's 2 things we want to know: the speed and the distance. Now what I would say is, whatever the question asks for, you may as well just work out everything because you never know later on what you're going to need. So I'm going to do V and I'm going to do T. To do V, I'm going to use V squared equals U squared plus 2AS. So V squared equals 3 squared plus 19.6, which is 2A, times 2.5, which is S. And if you work that out and square root it, it comes out as 7.62 meters per second. So when it hits the floor, I've got 7.62 downwards. Okay, negative really because it's down, but we are calling down positive. Horizontally, that's not going to change. So it's always been going at 35 meters per second. So actually already I could work out the speed. But I'm going to do time quickly as well. So the time it takes to fall, I'm going to use S equals UT plus a half AT squared for this. So we've got 2.5, which is S, is 3T, there's your UT part. And then we've got a half AT squared, so 4.9 T squared. Now I know a lot of people don't like using this equation because it makes a quadratic, but I'd rather do one equation than two myself. If you rearrange that to get 0 on one side, probably easiest to go over here. So 4.9 T squared plus 3T, and that's going to be a minus 2.5 when we tied it to the left-hand side. Now, obviously, when you solve a quadratic, you get two solutions. Okay, you can use your calculator for this because that's not going to factorize, is it? 0.471 and your other solution minus 1.08. Now, this is mechanics, not pure maths, so you can't have a negative time, so you can put a line through that straight away. So the ball will take 0.471 seconds before it lands. Okay. So how does that help us? Right, well, let's do the speed first of all, because the first thing we have to do is work out the speed when it bounces. So that means if I make a sort of a bigger version of my little triangle I've already drawn, we've got 35 horizontally, we've got minus 7.62 here. And again, this is just a Pythagoras and tan question. You do get bored of doing this when you've done a few projectile questions because they all seem to ask for it. The Pythagoras, so the speed comes out as 35.8, so that goes there, 35.8 meters per second. And then the angle, so this is tan minus 1 of O over A, comes out as 12.3 degrees. Okay, so that's this little triangle up here. Okay. Horizontal distance when it bounces. If I want to work horizontally, I need to transfer that time value over here. So the time is 0.471 seconds, and then we can just do distance equals speed times time. And then if you plug those numbers in, you get 16.5 meters. Okay, so from where the bowler released the ball, it bounces 16.5 meters further down the pitch. Okay, I mean, a little bit complicated, but you could then look at what happens after it bounces, but you'd have all sorts of energy losses and things. Okay, so we'll stop that question there. That's enough for A2 projectiles. Okay, now I want to have a look at something called the equation of the trajectory. Now, a trajectory is the path that an object takes, okay, and it's like plotting it on a set of X and Y axes, okay, just like plotting any other quadratic really, because that's all it is a negative quadratic. Now, why would we bother doing that? Well, so far, all of our calculations have in some way or another depended on time, okay, and sometimes you're not interested in time, you just want to know its position, okay. So when it's 20 meters away, how high is it? Or when it's 6 meters in the air, how far away is that? And that's what the equation of the trajectory is trying to do, is trying to sort of plot this path in terms of X and Y, horizontal and vertical. I've got my axes the wrong way around there. X and Y, rather than in terms of T, okay? And what you end up with is some quite complicated looking equations. And if I go through these now, we'll run out of time. So what I've got for you, if you want to like do a little pause and a scan, okay, what I found is a nice little proof. It takes you through exactly what I would have done anyway. There's a little YouTube video there of the proof of the trajectory formula. And you do need to know how to get that formula from scratch, okay? That is part of the spec. You are expected to know, okay? Now, what they'll say is prove that. So if you can't do the proof, you can still do part B of the question, but you will be losing 3 or 4 marks if you don't know the proof, okay? It basically involves working horizontally and making T the subject, and then putting that into the vertical equation, y s equals ut plus half at squared. Okay, now what I will quickly mention is why there are three versions. Okay, so this top version here, where you've got cos squared theta on the bottom, that's the one you would be using if you already know theta. Okay, if you know theta, and so there's four variables in this equation. If you've got three of them, so you've got y, which is your vertical displacement, x, which is your horizontal, you've got u, which is the speed that it initially had, and you've got theta, the angle it was launched at. So if you've got three of those, and theta is one of them, then you would use this top equation. So if you've got y, u, and theta, and you want to find x, easily done. Okay, not a problem. It'll make it quadratic, but you can find x. That's okay. The reason we need these other two, okay, and that middle one here is basically just a stepping stone to that one. It's not really one on its own, so you can kind of ignore that. The reason we would use the bottom one is when we've got y, x, and u, but we're trying to find theta, okay? And that's because if you look at the top equation, theta appears twice. That's not a problem, really. But what is a problem is that it's tan theta the first time it appears and cos theta the second time it appears. And you can't solve for tan and cos theta at the same time. So what we do using trig identities, and the first one we use is that 1 over cos squared is sec squared. And then the second one we use is that sec squared theta is 1 plus tan squared theta. What we've managed to do now is get the same equation, but all in terms of tan theta, and that now is solvable, and it will form a quadratic in terms of tan, okay, which means you can actually find theta now. Okay, so you need to know how to get this original one from scratch. Watch the video here. You also need to know how to use your trig identities, so go from cos to sec to tan for this one. Okay, now let's have a little look at the question, and I'm going to do one where we actually are going to find theta, because you don't really need the equation of a trajectory unless you find theta. You can just use what we've already done. So we've got a cannon. It's got an initial speed of 60, so u is 60. It's got a target that's 100 meters away, so x is 100, and that target is 12 meters off the ground. So we've got u, x, y, and what we're asked to find is theta. Okay. Now, you don't even need to bother finding the components because you just put these values in as they are. Okay, so let's get the equation of the trajectory in a format that lets us find theta. So that's x tan theta minus gx squared 1 plus tan squared theta, and all of that then is over 2u squared, and all you've got to do then is put in your values. So y is 12 and x is 100, so 100 tan theta. G is 9.8, so then we've got 9.8 lots of 100 squared. Okay, we'll change colour pen here, and then we've got our 1 plus tan squared theta there, and all of that is over 2 lots of 60 squared. That's the 2u squared part. Okay, now there's various ways you can rearrange this. The first thing I'm going to do then is I'm going to take all of the numerical sort of bits here, so that's all of that, and I'm going to see if I can make that a little bit nicer. So if you type all of that into a calculator as a fraction, that would give you 12 equals 100 tan theta, and it doesn't give you a great, it comes out as 245 over 18. Okay, it's a little bit nicer than what we had, and then you've got your 1 plus tan squared theta there. Okay, the next thing I'm going to do, because I don't want this fraction, is I'm going to multiply everything through by 18. So that gives me 216 equals 1,800 tan theta, and now we've just got, and I can expand this out now as well because it's not part of the fraction anymore. That gives me minus 245, and be careful because this minus affects everything, minus 245 tan squared theta. Okay, all we need to do now is tidy that up into something that looks a bit like a quadratic. Okay, so I don't want this negative tan squared if I can help it, so I'm going to bring everything over to the left hand side. So I've got 245 tan squared theta, and that's positive now. The tan theta term comes over and that goes negative, so minus 1800 tan theta, and then I bring the 245 and add it to the 216, and that gives me 461. Okay, equals 0. Now then, solve that like any other quadratic. Okay, A is 245, B is minus 1800, and C is 461. But what you'll be finding at the end of that is not x, it'll be tan theta. Okay, so if you put that into your calculator, the first value you get is 7.081, and the second value you get is 0.2657. Then you need to do tan minus 1, okay, to get it into back to theta. So this one comes out as 82 degrees, and this one comes out as 14.9 degrees. Okay, 3 significant figures. Why are there 2 answers? Well, what's happening there is, whoops, let me undo that, that's terrible. Put a straight line on. So here's our cannon to start with. Here's our target, which is 100 meters away and 12 meters up. What we're saying is there are 2 ways of doing that. We can go very steep, 82 degrees, and hit our target on the way back down, or we can go at a shallower angle of 14.9 degrees and do that. Okay, and both of those trajectories will hit the target of x being 100 and y being 12. Now the difference is the one which went up high will sort of land soon after, and the one which we hit at a flatter angle will go a bit further away over there. So if you actually want a bit of distance, you're better off using the more shallow angle. Okay, and if the only thing you're interested in is going a long way, then you want to go at 45 degrees. That's the optimum angle. Right. Run a little bit low on time, so I had a few more questions to do. So what I'll do is I'll just show you them quickly, and then I'll work through them and I'll upload the answers then to the resources section on the Carlin Cymru website. Okay, so on this one we've got just one particle being fired to start with, and it's going to land at some point B. So it's starting from A and landing at point B. So A's over here. Oh, hang on, wrong setting. So A's there, B's there, and it's going to do that first of all. Okay. Now then, in the second part, and this is a little bit trickier, so assume we didn't get time to do this. 1 second after A is fired, another particle is fired from B going the other way, and they collide. Okay. Now, if they were fired at the same time, they would meet in the middle. They would do that, and they'd smash right in the middle there. But because there's a time delay of 1 second, what actually happens is the particle that was fired first goes like that, and the particle that was fired second doesn't get to the top. Okay, and that's a little bit tricky. So I'll make sure I do go through that one and post it. Okay, this is very similar to the question we did with the cricketer earlier. So starting from a height, and the question is, does it go over the net? Okay, so, and that's in vector form, and that's from 2019. And then I've got one more then, okay, which is, does a golf ball pass over a tree? Okay, and you can see by asking us in part A to use the equation of a trajectory, that's the way they want you to go about this question. I mean, would you have a choice in that? No, because we don't have theta. Now remember, I said if you've got theta, you can get away without using the equation of a trajectory. But if you want to find theta, you have no choice. You need to use the equation of a trajectory. You need to use it in the format with 1 plus tan squared, otherwise you can't actually solve it. But once then you've got your angle, it's not a problem then to do the rest of these. And actually, I do have the marks there for that one, but again, I'll put that up on the resources section because we have run out of time, which is a shame. Okay, back to you, Mr. Mackenzie.
Thank you, Mr. Weatherhead, and I hope you all found today's session useful. We've got our last session next week, which will be focused on modulus and differential equations. and will be done by myself. Thank you very much again, and I hope to see you next week. Bye.